Hi there, it's Chem Coach Powers, and today we are going to be talking about types of chemical reactions. So this is going to be a fun lecture. You're going to see some pretty interesting things with regard to how some of these chemical reactions are being used on an everyday basis, and I think you're going to enjoy it. So let's go ahead and get rolling. This is section 8.2 in your book, and we are going to have these two objectives: to recognize 5 types of chemical reactions and classify the reactions by type. And then we're going to learn how to predict the products that will form in these simple chemical reactions. So, we're going to give you a couple different reactants, and then you have to guess what the products are going to be. We're going to give you some tricks and tips to help you figure out how to do some of that, of course. So, given a formula or equation for a reaction, you can classify the reaction as a single replacement, double replacement, synthesis, decomposition, or combustion reaction. And then given the reactants for a chemical reaction, you can determine the type of reaction that will occur, and then use the type pattern to predict the products of the reaction. All right, so let's get to it. We're going to talk about 5 basic types of reactions today. Now, each of these has a kind of like what we call a general form, which is like we want you to kind of recognize a pattern. All right. And so what we're showing you here are these different patterns. And of course, there's no element A or element B or element X, element Y. That's not what we're trying to point to. We're trying to point to if this is an element of variable A, whatever element that is, it's going to have this kind of pattern that you want to be able to recognize. So learn how to recognize patterns from actual elements that will fit this form. So the first type is decomposition, then synthesis, single replacement, double replacement, and combustion. And we'll go through each of these on an individual basis so that you can see what each of these is doing. So we'll start with decomposition reactions. The decomposition reaction is where you start with a single reactant and you're going to end up with multiple products, sometimes 2, 3, or more. Okay, so if you see a single reactant on the left side of the equation, that is your indicator, hey, this is a decomposition reaction. So look for that. Look for that single reactant. You know it's a decomp reaction. Let's see some different types. Now, these different types form some various different patterns, and these are shown to you in your book, and you would probably just want to be able to look at these and then recognize them. Especially for these decomposition reactions, you'll see that there are quite a few questions that you'll see in homework and tests and things like that that will ask you to recognize, what is this breaking into? And so for the first one, decomposition of binary compounds, meaning we're just breaking it down into its 2 different components. It's binary, and now it's separating out into its 2 elemental forms, okay? But you'll notice that not everything forms like that. In this next one, we have the decomposition of metal carbonates. And so this is calcium, that's the metal, with carbonate. What does it do? Well, it actually forms a metal oxide and then carbon dioxide. So this could also be true, for instance, if we had sodium carbonate, it would form sodium oxide and then carbon dioxide. Let's say we had magnesium carbonate, it would form magnesium oxide and carbon dioxide. So it will fit that pattern. The metal with the carbonate is going to break into a metal oxide and carbon dioxide. Okay, so that's the pattern for metal carbonates. For metal hydroxides, you can kind of see that pattern is very similar. Interestingly enough, it's still forming into that metal oxide, but now our other product is going to be water. So a metal hydroxide will form a metal oxide plus water. So again, this could happen. You see it right now with calcium hydroxide turning into calcium oxide and water. But let's say we had magnesium hydroxide in there. It would form magnesium oxide and water. Okay, so that's the form that we would be looking for. A metal chlorate. So here's the metal potassium with the chlorate. And what is it going to do? It's going to form a metal chloride and then oxygen gas. Okay, so again, we see it here with potassium chlorate forming potassium chloride and oxygen gas. But if this were sodium chlorate, it would form sodium chloride and oxygen gas. And then we have our decomposition of acids. So this is carbonic acid. This is the type of acid that we see in our soda drinks. Okay. We have that forming into carbon dioxide, which is where we get our little fizzy from our sodas, right? And then water. And so a carbonic acid, which is, again, one of the things that makes the soda acidic, that carbonic acid is going to break up into carbon dioxide and water. Now, what forms or what reason does it do that? Well, a lot of times it can just do that because of changes in pressure and things like that. So when I open it, then that extra carbonic acid that was in that solution would now all of a sudden be losing some of its carbonic acid as it turns into carbon dioxide. And you'd see the pH actually change on that too. All right, so let's look at some places where we'd see these decomposition reactions in our everyday life. We would want to speed up decomposition reactions if we wanted to try to eliminate things like toxic waste or other types of waste, fats. And of course, explosives is a fun one to think about. We'll actually hit this fats one here a little bit more too on the next slide. But explosives, think about it. What is an explosion but a very, very rapid decomposition reaction where the gas is suddenly being released at really, really fast speeds and it causes a concussion wave, right? So it causes enough of a blast of air that it can actually cause damage. And then we can also use decomposition reaction understanding in other ways. What if we can slow down the decomposition reaction? That would help us to slow down the rusting process or the aging process, right? If my body is aging, my face is getting wrinkles and things like that due to decomposition reactions, what if I can actually slow that process down? That would be pretty useful, right? Another perfect and great example, and we already showed you this example, we didn't give a name to it, for a decomposition reaction is electrolysis. Electrolysis is basically just taking a substance and like water and putting electricity into it, and that electricity is actually what's causing it to break up into its two different components. So you can take a battery, you can even do this with a 9-volt battery, stick a 9-volt battery inside some salt water, you'll see little bubbles forming on either side of those terminals. And this is a decomposition reaction. It's also kind of fun, I always like to point out that volume and that volume are different. That our reaction says that I'm going to make 2 hydrogen molecules for every 1 oxygen molecule I have. So if I actually look at the, that wasn't a very pretty arrow. If I actually look at how much of the gases are being built up here, I can see that this one has twice as much, which means that one is going to be the hydrogen gas, right? So that's going to be hydrogen. And then this one is going to be the oxygen. And that's really evident in this particular reaction because you can see twice as much gas. That little 2 right there is indicating there's twice as many moles of that one as there is of that one. Cool, huh? All right, so I told you there's going to be a little bit more about the fats part. This is the decomposition of a fat into oil. It's pretty cool. If you actually take, and these are turkey guts that you see on the left, if you take turkey guts and go through decomposition reactions with them, you can actually turn them into oil. And you could turn 600 million tons of turkey guts. That's what we get every year. At least that was back when this was first done. And other waste into 4 billion barrels of light Texas crude each year. So imagine that if we could take all the turkey guts that we create in this country and then just go back through and reprocess it. Wouldn't that be fascinating? Wouldn't that be cool to be able to create 4 billion barrels of oil from turkey? Now, you're like, well, why don't we do that? By the way, this process is called depolymerization because those turkey guts are in long chains, right? The fats are a long chain of molecules. And to depolymerize it, to turn it into small little chains of molecules is what you would have in the oil. Why don't we do that? Well, we can, but it's pretty expensive. If we could do it much more cheaply, then that would be worthwhile. We could actually get oil that way, but it's actually cheaper just to get oil from the ground, right? Another really cool process. Think about what we could do if we were able to take other types of plastic products, right? So remember, plastics are basically made out of oil. And if we go back and we can recycle them perfectly and get them all the way back to other types of materials again, what would that actually turn into? This is kind of a fun way to look at this because I could take 100 pounds of plastic bottles and I would produce out of 100 pounds of plastic bottles, I could make 70 pounds of oil, 16 pounds of gas, 6 pounds of carbon solids, think about like charcoal or something like that, and 8 pounds of water. Wouldn't that be wild to just take that plastic and actually turn it into things that I could reuse just like that again. Again, can you do it? Yeah, I can kind of show you the process here. It goes into a grinder and it goes through various different types of reaction vessels to give you the materials that you want. But again, really expensive. And, is it worth it, or is it easier just to pull the oil out of the ground? Is it easier just to pull the water from the lake, right? I mean, these kinds of things can be done. And someday, if our world has gone to that point where we just don't have any more, resources, then yeah, this is probably going to be the only way to get these materials. At this point, we still have lots of natural resources left on this planet. But if we can start using processes like this, and we can get through this process with low energy cost, then this could actually be really great, because then we aren't dealing with a lot of pollution, right? Wouldn't it be great to have, these products that we can actually use instead of having plastic bottles floating around in the ocean, that kind of thing, right? Kind of cool to think about. Tires. Think about what you could do with all the tires that we use every year. Yeah, wow, 57 pounds of water. Woo, for 100 pounds of tires. Our tires are made up of a lot of water, right? And I didn't really think about that before, did you? Oh, sorry, that was liquid waste. No, that makes a lot more sense. I'm like, what? 57 pounds of water from tires? Okay, yeah, 4 pounds of water. That makes a lot more sense with tires. Okay. And then we have things like heavy oil, and then medical waste. I think that one's kind of interesting. Think about all the nasty stuff that hospitals have to get rid of, what kind of things you can get from that. Anyway, just a fun slide. You're not going to be tested on that. It's just kind of cool to look through. All right, so let's look at our next reaction type. This is synthesis. And the general reaction can be seen here. A plus X gives you AX. Again, the thing you want to look for here is a single product. If all you have is a single product on the right-hand side of the reaction, this has got to be a synthesis reaction. I'm starting with multiple things and I get one thing. Now, I will tell you that there are other types of synthesis reactions. And so, for instance, we might have one that's like in photosynthesis. And when you have things like photosynthesis, we still call them synthesis reactions, even though there might be more than one product, because you're still putting things together. So we are going to define it in our test as a single compound being made on the product side, right? And then you might have 2 or more reactants. But I just want to tell you that you will see other types of synthesis reactions in chemistry. They're still considered synthesis, even though they have more than one product. Where do we use these? Oh, medicine is a big one. Flavorings. You're going to love the slides that I'm about to show you about flavorings. It's just a lot of fun to think about the kind of synthesis reactions that make the flavors that we're used to. Plastics, high energy fuels, all of these things are a result of synthesis reactions. So check this out. Synthesis of flavorings. Now, we're starting with acetic acid, okay? And so we've got this acetate ion that we've talked about and learned about before, and then the hydrogen ion, right? So that's making acetic acid, which is vinegar. And so this is basically what's going to happen. That vinegar is going to basically be the product of a lot of these different synthesis reactions that make all these different flavors. And so I want to show you that. So this right here is also the vinegar, right? So this molecule here is the same thing as this molecule here. Okay. Oh my goodness, look at this. It's the same thing as this molecule here. Anytime you see a little place where something comes together like this in a skeleton type of formula or ball and stick kind of model, this is structural formula, there's going to be a carbon molecule, right, or carbon atom right there. Okay. So this isn't ball and stick, but the structural formula that you have, if you just see little points, those points are going to be the carbon atoms from the, this is basically an organic compound, the way that we write organic compounds. Anyway, you got to check out some of these really, really cool reactions. Okay. And again, this process is called dehydration synthesis that we're about to talk about. And you'll notice again that these kind of don't exactly fit the model of having only a single reactant, but super, super cool. So if we take propyl alcohol and acetic acid, we're actually going to make the pear flavoring. Okay. I'm not sure where I have my little labels in here, but they're gone. But yeah, so we have made a pear flavoring from taking propyl alcohol and acetic acid. All right. I'm missing some of my little labels here. So I'm going to come back Okay, there we go. All right, so now let's look at this one. We have octanol, which is basically gasoline, and we put that with acetic acid. We get our orange flavor. What? Gasoline gives me orange flavor? Yeah, it's kind of cool. Benzyl alcohol, that's the stuff you see in lava lamps, plus acetic acid gives you the flavor for strawberries. What? We've got the juicy fruit flavor coming from an isopentyl alcohol, pentanol alcohol with acetic acid. We've got, this one's kind of gross, rancid butter, butyric acid. Basically, it's the main component of rancid butter, or one of the main components that makes it smell and stink. You take that with some ethanol, just typical liquor, and you're going to get your apple flavor. What? Okay. Oil of potato spirit. Okay, basically amyl alcohol, and salicylic acid, which they use in taking out warts. You put those together and you get your pineapple flavor. Now you might be going like, oh, this is so gross. It's not really that gross. Remember, chemistry is amazing, that you're going to take these different chemicals, you rearrange all the different atoms, and you get completely different characteristics. Remember that a compound that is going to have different characteristics than its original components, right? So we get all these really, really amazing things just by rearranging the molecules around. And it's not gross. It's not rancid butter anymore, all right? That's like saying hydrogen peroxide is the same thing as water. I'm drinking hydrogen peroxide when I drink H2O. No, you're not. It's H2O and H2O2 are very different things. All it takes is one little change, one little extra oxygen, and completely different chemicals, right? Well, the same thing here. It's kind of gross, but kind of cool to see what kind of flavors we get off of these things. And this is really literally how they would make these. Now, for candies, okay, this isn't like this apple flavor. This is an apple flavor you'd put into a Jolly Rancher or something. This isn't like the apple that you eat, okay? All right, now notice that there's a water. Each time I told you that this reaction was called a dehydration synthesis. And what we're doing is we're getting this molecule over here is the molecule that's the result of our synthesis. All right, it's putting these guys together. But what happens is it always takes off like a hydrogen from one and a hydroxide from the other, and that forms the water, and the rest of it forms the other compound, right? So this is pretty cool. It's called dehydration synthesis, and it's making a water molecule at the same time it goes through the synthesis reaction. All right, so here are a couple other flavors that you can see. Just kind of fun to see the process here. Wintergreen, banana, etc. This cool stuff. All right, so how does this reaction work? I wanted to kind of show you a little visual of this. So these are the two little chemicals that we're trying to put together. We're putting together this chemical and this chemical. And watch how the water molecule leaves. You see how that water molecule left there? Once that water molecule leaves, then these two chemicals can actually come in together and bond. Let's show it again. Here comes another one. Now notice again, this one has the red atoms on it instead of the green ones, but that still same kind of thing happens. We've got some synthesis reaction where a water molecule is going to leave. So again, this is dehydration. We lose the water. Dehydration synthesis. And finally, one more time, comes in, we lose the water, and we end up having the new molecule form. So it forms into long change. It's going through a process called polymerization as it does that. Okay, let's talk about single replacement reactions. This is our next type of reaction. And this one's pretty cool because this one has to do with single elements reacting, and they're going to form a new element, okay? So the general form is A. That's the single element. Oh, lost my little marker there. I don't know what happened to my pen. I'm using the eraser. All right, so we've got the A, and that's the single element forming with the BX. That's the compound. Now, notice that what's going to happen is this is going to be a swap. Okay, they're going to switch places. And so the A is going to join up with the X instead of the B. Okay, so now we have AX, and then the B gets replaced. What's happening here is that this is the more active element will replace the less active element. So B is not as active, and so A replaces it. This is going to be covered in section 8.3. It's about the activity series. And for this particular reaction, I like to think about it kind of like dancing partners, okay? So it's kind of like, you know, Alice comes to the party all by herself, and then she sees Brenda dancing with Xavier. Okay. So we've got Alice, that she's a single element, and then we've got Brenda. Brenda and Xavier are the couple. And as they start to dance, Xavier sees Alice and is like, oh, I like Alice more. And so when they swap partners, now we become a new partner of Alice and Xavier. It's the new couple. And then unfortunately, Brenda is no longer with Xavier. She just lost her date. But there might be another guy around that, she's going to hang out with now. But that's the way I like to think about these single replacement reactions, is that one of the reactants is more attractive. And the one that's more attractive, or in this case, more active, that's the one that's going to replace the one that's not as active. And we look at a table, there's this called this activity series table, and we have to look at that table to see if this is actually going to happen. Because guess what? Brenda might be more attractive. And so if Alice comes in and Brenda's more attractive, Xavier is going to be like, no, I'm not going to be dancing with Alice. I'm going to stick with Brenda. And so if that happens, and if there's no reaction, we just type in NR. Okay, it's no reaction. This doesn't take place. Brenda's more active than Alice, or B is more active than A, and therefore this reaction will not take place. It will not go to completion. It will not be happening. That's the kind of thing that we would write if we saw that taking place. All right, remember, the same type of element must displace the same type of metal. So a metal can replace a metal, a non-metal can replace a non-metal. But don't, I see this happening sometimes. You might have like sodium plus potassium chloride. And then students are like, oh, yeah, that's now sodium, potassium plus chlorine. That's not going to be the case, right? Because the metal's got to replace the metals. That's not right. It would have to be the sodium getting in there and replacing the potassium. And then potassium is the thing. It's supposed to be a K that's left over. Okay, so make sure you replace metals with metals. Make sure you replace non-metals with non-metals. Really cool application to this is batteries. When we look at a battery, we want to see that one ion is replacing another ion, and this movement of this ion is what gives you this electric current, this charge. And so in this example, we have zinc and copper phosphate being put together, and the zinc is more active than the copper, so the zinc is going to replace copper, and so you now have zinc phosphate, and then the copper gets left out. And this is how batteries work. Okay, the battery, and this is kind of fun to think about. You've got a battery here made from a whole bunch of potatoes and some nails and the copper. Now the nails have got zinc in them, and the copper is, the other parts that are kind of chunked in there. I don't know if you can see it, but like there's a little chunk of copper stuck into the potato, and then there's the chunk of zinc stuck in the potato, right? So you've got chunk of copper, chunk of zinc. And so what's happening is this potato is giving a little pathway for that copper to be replaced by the zinc, and it creates a small little electric charge. Potatoes can be little batteries if you use two different types of metals that allows those metals to move back and forth between them. And if you take it and you make a big, long series battery, one potato after another potato after another potato after another potato, you put all of that into a big area. Okay, you can see this truck now has all these potatoes in it. You can get like a charge. It's not even as big as a 9-volt battery, but it's kind of cool. Each potato generates about 0.5 volts and 0.2 milliamps. So the entire 500-pound battery generated only 5 volts and 4 milliamps, which again is not even as much as a 9-volt battery, but neat to see that you can increase that that voltage output as you do it. All right, here's another example of a single replacement reaction. This is where we're having to look. We have an ion, okay, that is connected with nitrate. So this was silver nitrate, and copper is coming in. Is copper more active than silver? If it is, then the copper is going to come in and it's going to replace the silver. And so now in this case, silver is able to form its own little stable compound, and it gets replaced. And so their silver comes out of solution. So what we're seeing here, we've got this little copper wire, and as it's sitting inside this silver nitrate solution, then the copper is actually joining into the liquid. It's going to become a little bluer as time goes by, and then the silver is actually precipitating out. So there's silver that's coming out of solution there, basically. All right, let's look at double replacement reactions. Okay, so now we've covered 3. Let's go into the 4th one. We've got 4 and 5 to cover still. A double replacement or double displacement reaction. You'll probably hear me say double replacement more often than double displacement, but they mean the same thing. Now it's like these 2 couples have come to the dance together, but then they actually find that they're more compatible with the other couple, and so they swap partners and go home with different partners, right? And that's what we're having here. Now, the AX and the BY come to the party together, but A goes home with Y, B goes home with X, okay? Why does this happen? Well, it happens or is driven by the formation of solid precipitates that are insoluble, gases that are going to come out of solution, or molecular compounds. A lot of times water is going to be the molecular compound that comes out of this solution. So if you're forming a new substance that's no longer soluble, that's what actually is driving this reaction. Okay, that's why these things will swap partners, because they find new stable formations that are no longer actually attracted to the water molecule. They're more attracted to themselves, to each other, than they are to water, as water would not try to pull it out and make it a part of the solution. It doesn't want to be part of the solution. And so whether it be carbon dioxide that leaves, or whether it be a solid precipitate that falls down to the bottom, that is what's going to happen here. So again, the whole idea here is that one of these products is going to be insoluble. In order to know if this is what's happening, we would check a solubility table. Now, I'm going to tell you next semester we'll use the solubility table. We're not using it right now. Don't worry about the solubility table at this point, but know that in the future, you'll know whether or not this reaction actually takes place or doesn't based upon a solubility table, okay? All right, so let's look at some of these as examples. Here I have barium chloride with magnesium sulfate. And what happens is it forms this barium sulfate, which is insoluble. Okay, it's a solid. Now that it's going to be, formed into this new thing, it's no longer able to be dissolved in water. And so because I have this new substance that's being formed, this is a double displacement reaction. And what drives it? The formation of this solid precipitate is what drives it. And so notice that all of these barium, we'll start with this again, magnesium and magnesium are ions, and then chlorine and chlorine are ions. And then you'll notice that the barium is an ion on one side, but it's combined over on the other side. Sulfate is an ion on one side, it's combined on this other side. And so the magnesium and chlorine are considered spectator ions in this reaction. We'll learn more about that later. But what drives this reaction is that barium and sulfate want to get together. And so magnesium and chloride go home together. I want barium sulfite go home together. All right, so there's another example. Lead nitrate reacting with potassium chromate gives you lead 2-chromate and potassium nitrate. So this is a cool one because you can take these liquids, and what happens is this yellow solid is precipitating out of solution. It falls out of solution, tiny little yellow powder that's basically inside that solution at the time. Another example, nitric acid. If you were going to try to do, and we do this at the end of the year, on normal years, we make some silver Coke bottles. One of the ways you can do that is you can make some silver nitrate, okay, and then react it with the magnesium nitrate. And oh, that's not right. Silver nitrate plus, here we go. Silver nitrate plus sodium chloride. It's going to give you silver chloride plus sodium nitrate. That's an example of a double displacement reaction. This one up on top, that's not quite the reaction that we use when we do ours. And so I'm not sure exactly what reaction that one is using. It's not looking like a double displacement reaction, is it? We have two products on the right side, but they're not telling us what's on the left side. So anyway, this one here on the bottom, silver nitrate plus sodium chloride, you can see that we've definitely swapped partners. The nitrate over here is now with sodium instead of with silver. And notice that this is the solid, that's the solid precipitate that's coming out of solution in this case. All right, so I think, yeah. Let's look at another type of double displacement reaction. We've got sodium hydroxide reacting, and it's reacting in this case with just some vinegar. We talked about that acetic acid before, and it's going to form sodium acetate and some water. Okay, so sodium hydroxide is the kind of stuff you'd see, for instance, in your Drano, your liquid Drano, and then your vinegar is, you know what vinegar is, and you're making sodium acetate and water. Now this is kind of cool because this is a food preservative. This is one of the things we use to demonstrate supersaturated solutions and watch the crystallization of the substance come out, but it's used in food preservatives. Another good example of a neutralizing double displacement reaction, and I want you to remember and focus on the fact that this is called a neutralization reaction, okay? So it's a double displacement reaction. It's a very particular type of double displacement reaction, though. It's called a neutralization reaction or a neutralizing reaction. In this case, we're neutralizing a corrosive like hydrochloric acid. Muriatic acid is kind of like the name of hydrochloric acid when you buy it at the hardware store. You've got hydrochloric acid plus sodium carbonate, okay? And then that's going to form sodium chloride plus carbonic acid. All right, so you've basically made this substance much safer. Hydrochloric acid is a pretty dangerous caustic acid. Carbonic acid is not that big of a deal, and that's just going to decompose. And the next step, that goes through a decomposition reaction, right, where it forms hydrogen, some water and some carbon dioxide. So some other types of double replacement reactions. Okay, finally, our last one is a combustion reaction. And we want you to remember that this is a carbon-based compound. Oftentimes, it's going to take the general format of CXHY. So, for instance, I might say C3H8 or C2H2. Any sort of CH combination is typically what we start with in these. And if those react with oxygen, then you're going to form carbon dioxide and water. Okay, so the products of a combustion reaction in this case, in this example, are carbon dioxide and water. So look for that. If you see the two products being carbon dioxide and water, it's a good chance that it's combustion. If you want to make sure for sure, then just make sure that you've got carbon over there on that left-hand side, right? It's got to be a carbon-based compound that you start with, and oftentimes it's a hydrocarbon. Okay, when hydrogen and carbon are together, we call those hydrocarbons. And so if you see that, then this is a combustion reaction. Now, combustion reactions are defined a little bit different depending upon what book, what source on the internet you might be looking for. But the example that we're going to talk about, our combustion reactions, are carbon-based compounds that are going to react and give you carbon dioxide and water. They generally are going to give off energy. Okay, that's another characteristic of combustion reactions. They're generally going to give off energy, right? So you can think about these things as burning. If I'm burning some of this propane, right, that's going to be a combustion reaction. So these things are going to be giving off energy typically as you go through. And so what do we do to think about these for practical purposes? We can make cleaner burning fuels. We can make better fireworks. We can make antiseptics, hyperbaric chambers. These reactions can help us, right? Do we want to have oxygen in that chamber? Hyperbaric chambers above the pressure, high pressure chambers, right? And then what can we also do with these combustion reactions? We can resist oxidation reactions. Okay, so if we can oxidize something, we are losing electrons. We'll learn about that later on. A combustion reaction, in this case, we're almost, kind of doing the opposite. And so it's a way to try to slow down the oxidation process. All right, so we need to be able to match these up. So I want you to take a second and just draw lines from one to the other and show me that you know what you're doing. So we're going to pause it. And you're back from practicing. Let's see how you did. This has got a single reactant, and so that's got to be the decomposition. Single product, that's got to be synthesis, right? Single displacement, yes. Double displacement, no, that's not what this one is. This one is a combustion reaction, right? It's got carbon dioxide and water as the products. And so this one here must be our double displacement reaction. Okay, so hopefully you guys got that. Let's go on to our next one. These are ones that I want you to try to identify the type and then also balance it, okay? So we'll just pause and practice here and come back and see what the answers are. Pause it. And we're back. And so this one has got a single product. And so because of that, we know this must be synthesis, right? It's got O2 here, so I've got to put a 2 there, and I'll have to put a 2 there. This one's got a single reactant, so that means this must be decomposition. Okay, so what did we say this one was? This was synthesis. This one's decomposition. And so we've got one oxygen here, but two oxygens here. We'll have to put a 2 in front of that, a 2 in front of that. This one's got aluminum, and in this case, it's copper with chlorine, but copper gets replaced. Oh, poor copper got replaced. And so we've got to balance this. This is a single replacement or single displacement, but we're going to have to balance it. I've got 3 chlorines on this side, so I want to make least common multiple, and so I'll have to do 6 for both of those. That means I have 3 coppers, and I have to have 2 aluminums. So that's that one. On this one, I've got partner swapping. Look, my lead is with iodine on this side, but it was with nitrate on that side. So this must be a partner swapping kind of equation, which must mean that this is a double displacement or double replacement. And so I've got to balance that. I've got 2 nitrates there, so I better have 2 nitrates there, which means I need 2 sodiums, and that's going to balance that out. And then this one has got products of carbon dioxide and water, which must mean that this is a combustion reaction. Now, combustion reactions are oftentimes a little bit harder to balance. So let's look at what we've got. We've got 4 hydrogens on this side. We've only got 2 on this side. Let's go ahead and try to balance that. I've got 4 hydrogens and 4 waters now. And on this side, I've got 4 hydrogens and, sorry, I said waters, oxygens. Okay, on this side, I have, try that again. On this side, I have 4 hydrogens, but 4 oxygens. 4 hydrogens and 4 oxygens. On this side, I have 4 hydrogens. And then I've got 5, well, right now I have 3 oxygens, right? And so my carbons are balanced, though, so I'm okay there. Got 1 carbon on both sides. And so what do I have to do to balance it? Well, I'll tell you, remember that these are a little bit tricky sometimes. These combustion reactions can be a little trickier, and you can do a little cheat method here. Is there something that I can add to this oxygen that's free to make it so that I get 1 more than I have over there, right? So what if I add, instead of adding a full 2, which would get me up to 5, what if I added 1.5? Does that do it? I've got 3 now, plus the one I have there is 4. Oh my goodness, that does it, right? And so now I've changed that up and I've got 4. And so what you need to do, you can't leave a half when you're doing these types of balancing. So you're gonna have to double everything through. And so you'd be like, oh, okay, well, I've got to double this to a 2 because that was a 1. This is a 1.5. I got to double that. That becomes a 3. This was a 1. I got to double that. It becomes a 2. This was a 2. I got to double that. It becomes a 4. And so your balanced chemical reaction is now 2, 3, 2, 4. So combustion reactions are a little trickier to balance sometimes, but you can use that little method. It's actually really helpful. If you can put a half on it for those oxygens, sometimes that works really well. All right. Let's try another one. Copy and balance each equation, or these equations, then state the type of reaction. So I'm going to give you a chance to pause and practice, and pause it. And we're back. Let's see how you did. This is going to be a synthesis reaction, right? Because we're putting things together. I've got 2 oxygens here, but only 1 there, so I'm going to have to put a 2 there and a 2 there. This is a single replacement reaction, so we'll just do SR in this case. And I've got 3 chlorines here. So I'm going to have to put a 3 there. Oh, but that means I have 3 and 2. That's not going to work out. So let me see if I can bump that up. Maybe I can make this maybe I can make this a 3, and then make this a 6. Okay, and then I can double that, and then I can double that, and we can see if we're all balanced. I've got 2 aluminums. I've got 6 chlorines, 6 chlorines, 6 hydrogens, and now we're all balanced. Okay, so that's the way you would do that one. Did you get it right? Are you a stud? All right, so now we want to go into how do we predict the products of a chemical reaction? Because again, this is not easy. We've got to be able to predict products of chemical reactions, and that takes a little bit of doing. So let's see what we have to do. Now I've got a table here, which is a kind of like a flow chart, and you can kind of follow this flow chart. So you can print this out online and then fill it in, and then you can use this the next time you're practicing how to actually categorize certain ones. We're just going to go through it step by step. So we'll stop at the top. Is there only one reactant? If there's only one reactant, then we know that's got to be a decomp, right? Whoa. Wow, that was pretty. So that's got to be a decomposition reaction. The general form is, like let's say we're starting with AX, and it's going to give us A plus X or something like that, right? Possible products. So when we're looking at possible products, what we're trying to do is we're trying to identify, what kind of reactions do we get. Remember, we had all sorts of ones with the decomposition reactions. We had, the decomposition of a metal carbonate with the metal hydroxides. We've got all sorts of different types of products that we had over here. But you remember carbon dioxide was a common one in the metal carbonates. Remember, we had metal hydroxides, and when we did the metal hydroxides, water was a common one. You can have various different types of typical possible products here, but one of them is oftentimes going to be elemental as well, right? So don't forget that. Okay, let's go to the next one. If there's only one product, then we can fill this out, right? And if there's only one product, we've got synthesis reaction. The general form is A plus X or A plus B gives us AX. Possible products, again, this is infinite, right? Lots and lots and lots of, not infinite, but it's got like very, very, very many different types of possible products. We're not going to go into, exactly what kind of possible products you'd have there, because you'd have a lot of different types of possible products. All right, so then let's go into this next one. Oxygen, it says, is oxygen one of the true reactants, and is the other reactant a hydrocarbon or hydrocarbon-like compound? So this sounds a lot like combustion, doesn't it? Because we talked about carbon dioxide and oxygen being a product of a combustion reaction. And so this has got to be a combustion reaction that we're dealing with. And the guaranteed products, again, oxygen is a guaranteed product, and water is a guaranteed product, and carbon dioxide is a guaranteed product. And a general form is, again, CXHY plus oxygen has got to be one of the reactants, right? Is going to give you those two products there. Okay. And so when we, I don't know, it kind of doesn't look like a Y, does it? When we talk about our general form, again, it's always going to be your carbon dioxide and water. So this is a really easy one to recognize. Is the elemental substance reacting with an ionic compound? Okay, so with this elemental substance, that's the key here. So we must be talking about, element A plus BX is going to be reacting and giving us element B plus AX, right? So this is a single replacement or single displacement. Possible products, again, you got so many different types, but one of them should be elemental, right? So you should be looking to find one of them is going to be elemental. Just like we started with an elemental, we should be finishing with an elemental. How do you know if a reaction will occur? Well, we have to look at our activity series. Again, I haven't showed that to you guys yet, but in order to know that this will take place, you have to check your activity series. All right, and then let's look at our last one. It says two compounds should be reacting if one of the reactants is one of the reactants a metal hydroxide and is the other reactant an acid. If that's the case, then this is a special type of, this is double displacement, but it's a special type called neutralization. right? So the neutralization reaction is, again, the same form. AX plus BY gives you AY plus BX. They're still swapping partners, but the key here is a metal hydroxide. So what is a metal hydroxide? Something like calcium hydroxide would be a metal hydroxide, sodium hydroxide. So is it a metal hydroxide and then an acid, meaning that it starts with H, like H2SO4 or HCl? If those are, part of your products, part of your reactants, then you're going to end up having, a neutralization reaction. And our results of a neutralization reactions are water and a salt, various different types of salts. So finally, we come to our normal, if it's not that type, it's just a normal, regular old double replacement or double displacement reaction. And again, that form is still the same. AX plus BY gives you AY plus BX. And products can be lots of things, but one is going to be insoluble, right? One's going to leave as a gas or be a precipitate. If you've just got to pay attention to the fact that one of them is going to turn into a liquid, gas, or solid. How do you know if a reaction will occur? Again, there is a solubility table that we will look at later on, but we haven't showed you that yet. So right now, we just assume that they all occur. Okay. Woo. All right. So that's how you can determine if reactions take place. Here we've got an example: aluminum oxide. What's gonna be its final breaking up place? Like, how does it form? Well, if we go look at the decomposition reactions, we can see different types. There is only one reactant, so we know it's decomposition. So it's probably going to form into its aluminum oxide components with just aluminum and oxide. Okay, so that's example one. Let's try some more. And again, you can pause and practice these. Hydrogen and chlorine, you've got a single reactant is basically what it's trying to show you over here, right? Sorry, single product, which is trying to show you. So does it only have one reactant? No. So we're probably getting one product? Yeah. So this is a synthesis reaction. And what is our final product going to be? It's going to just be putting the two together. This is binary, so it's just going to be HCl. Example 3, we've got methane and oxygen. I see this little oxygen here, and it's with a hydrocarbon, the CXHY, which means we probably have a combustion reaction. All right, do we have only one reactant? No. Do we have two elements reacting or only one product? No. All right, so again, what we're doing is just going through that flow chart here. So if you're follow through the flow chart, oxygen is one of the reactants and the other is a hydrocarbon. So this is combustion. And what are our products going to be? Carbon dioxide and water. Again, just follow through the flow chart as you go through. Example 4, only one reactant? No, definitely not. Two elements reacting and only one product? No, we don't have only one product. At least doesn't seem like it here, right? Is oxygen one of the reactants and the other hydrocarbon? No. So is the element reacting with a compound? Yes, an element is reacting with a compound. Therefore, we have a single replacement reaction. What are our products going to be? Well, let's swap them. We've got to check the activity series first once we do that. But for right now, you can just assume that they're going to swap places if I don't give you an activity series. And so you'll end up with calcium and aluminum phosphate being the products. And then example 5, only one reactant? No. Two elements? No. Oxygen? No. Element reacting with compound? No. We have two compounds reacting. Yes. So this is double displacement. Magnesium nitrate and silver chloride. They've got to swap partners. So those will be our new compounds. Don't worry about whether, which one is a solid. You'll learn about that later on. All right. So, we've done a lot, man. We went through and covered a lot, but now you can recognize all 5 types of chemical reactions. You can classify the reactions by type, and you can predict the products that will form in these simple chemical reactions. So if I give you a formula equation for a reaction, you can classify the reaction as single replacement, double replacement, synthesis, decomp, or combustion. And then if I give you just the reactants, nothing else, you're going to be able to determine the type of reaction will occur by going through that little flow chart, right? And then you can use that type pattern to predict the products of the reaction as well. All right, so It was a lot, but it was really cool. Lots of great stuff we got to learn about chemistry today. I hope you had a great time. I hope it was awesome for you as it was for me. Actually, I hope it is even more awesome for you. You're going to see these types of equations in your lab. Now you can do that lab on chemical equations or chemical reactions, sorry, and you're going to be able to fill out that far right column with all of these different types of reactions that you're doing in the lab, okay? All right, have a great day. God bless you, and be kind to one another.